Section 4.2, whoever happens to be watching. The mean value theorem, very, very important theorem. Luckily, it's easy to understand. But there are some stipulations to it that are extremely important that you pay attention to, specifically the hypothesis of the theorem. You remember this at all from geometry, hypothesis?
Yeah.
Hypothesis is the stuff that comes between if and then.
Oh.
The conclusion is if that condition is met, then this must be true.
Oh, of course.
And there are two hypotheses. There are two hypotheses to this theorem. It's on page 196 if you want to get there. And it's right at the very beginning. They present the theorem right off the bat. And this is what we call an existence theorem. We'll discuss that more in detail in a few minutes. But the hypotheses are the stuff written in the words. And here's what it says. And it's a lot. It's a lot to take in. So I'm going to go slow. If y, which equals f of x, whatever you call it, is continuous at every point of a closed interval, a to b, and also differentiable at every interior point. In other words, differentiable in the open interval from a to b. Then, here comes the then. So those are the two hypotheses. It has to be continuous on the closed interval, and it must be differentiable on the open interval from a to b. If that's the case, then there is at least one point C in the open interval from a to b. That means C between a and b on the x-axis, at which the derivative at C is equal to the slope of the secant line. Geometrically speaking, it means that the slope at some value, the slope of a tangent line at some value C, is equal to the slope of the secant line from a to b. This is a continuous function from a to b, and it is differentiable at every place you can see it, even beyond a and b. But in the open interval from a to b, it's differentiable. It has a slope at every single point. It's differentiable everywhere. It's also continuous. What we're saying is that if you find the point on the graph that associates that's with a, this would be f of a over here, and b, which is about right here, f of b would be over here. Then if you found the slope of this secant line, we'll call it m because that's what we're used to doing when we have 2 points, then there is some point C somewhere between A and B, such that if you found the tangent line, let me see if I can figure out what it would be about. If you found the tangent line right there, for example, no, that's not great. Let me try it here. This would be, well, this is C here. And in calculus, we would say that this, the slope of this line is f prime of C. Then somewhere in this interval from a to b, there is a C value such that if you derive it at C, this function, that the slope you will get will be the same as the slope of the secant line. Okay, so here's in a summary what it says. If continuous on a to b closed and differentiable on the open interval, then we get this equation. The derivative at C, in other words, the slope of the secant line at C, is equal to the slope of the tangent line. There's at least one C value, and it's always between A and B.
Why is this so important?
It's coming up.
I don't know, it just doesn't seem that significant to me.
I know, and you may not believe it's very significant even when this section's over. But we'll keep referring to it as we go through this chapter, and you will see its significance, and it will build in your brain as we go. It seems kind of stupid, and it seems kind of obvious, and it seems kind of easy, and it seems like, okay, so what now? Well, it's coming, and that's an excellent question, but it's an extremely important theorem. We're going to play around with it a little bit to make sure that you understand completely. I hope you understand completely what's going on here. Maybe not as important yet, but what's happening. So, if you look at the paragraph just below example, or just below the theorem, there's a lot of important things in this. And if you want to circle and star some things or underline some things in your book, it's fine. You can, for study purposes later. Here's what it says. The hypothesis of theorem 3 cannot be relaxed. Remember the hypotheses? Continuous and differentiable on the closed and open. Yeah.
Why is it specifically continuous at the closed and differentiable on the open?
You'll see that in a moment too. But what we're saying is those hypotheses have to be met and they cannot be relaxed even one little bit. The hypotheses of the theorem 3 cannot be relaxed. If they fail to be, if those things fail to be true at even one point in the interval, then the graph may, and I have the word may underlined because you guys, as soon as you start doing the exercises, are going to go, why does this work now? I mean, it totally negates the theorem. You'll see in a minute. We'll talk about it. The graph may fail to have a tangent parallel to the chord. He's talking about secant. For instance, the function, absolute x, is continuous on the interval from -1 to 1, isn't it? And differentiable at every point in the open interval except 0. And the graph has no tangent parallel to the chord AB. Look at this picture right here. I'm talking about the first picture right there. There, see what they've got? You draw a tangent line from A to B associated with -1 and 1, not a tangent line, a secant line, that red line. There is no tangent that is parallel to it in that interval. Because the open interval, differentiable in the open interval failed at a single point, 0. And so the theorem fails there. Let's take a look at the next one. The graph has no tangent parallel to the chord. Okay, wait. The function g of x equals int x. Right next to it, a little piece of integer x, just a little tiny piece of it. If we look at the interval from 1 to 2, it is not, it is not continuous on the closed interval, right? It fails to be continuous at 2. Got to jump discontinuity right there. Got a hole, however you want to visualize it, it is not continuous at 2. So it is not continuous in the closed interval from 1 to 2. And sure enough, if you draw a tangent line from the point that's on the graph at 1 to the point that's on the graph when x is 2, you get a slope of 1. And there is no tangent line in int x that has a slope of 1. We clear? You see how that fails? Now you might start thinking, based on these two things, that if any part of the hypotheses fail, any of this stuff fails to be true, then there will not be a C value. That's not true. You're just not guaranteed to have one. There may or may not be one. So listen carefully to this, because it's going to happen to you on the exercise, and you're going to wonder what in the world's going on, because it seems to negate the theorem, but it doesn't. The theorem says, if it's continuous on this and differentiable on this, then you're guaranteed to have a C between A and B for which this is true. If any of this fails to be true, there may still be a C. It's just not guaranteed, that's all. Which makes us feel like this theorem's even weaker. But you'll see. Just have faith. It'll come to you. You'll see.
I have faith. I can see.
Okay, listen up. It says, example 1 says, show the function f of x equals x squared satisfies the hypothesis of the mean value theorem on the interval from 0 to 2, and then find the solutions. Oh, that's interesting. I forgot to, I didn't finish reading this up here. This is kind of weird too. This also feels like a weak theorem. So take a look. The mean value theorem, listen. The mean value existence theorem, I have that in italics. It tells us the number C exists without telling us how to find it. It just says there is one. We can sometimes satisfy our curiosity about the value of C, but the real importance of the theorem lies in the surprising conclusions that we can draw from it. So, it's not the theorem itself. It's the interesting conclusions that we can draw and get from knowing this. So look at example 1. Again, let me read it to you. It says, show that the function y equals f of x. You got a good picture of that in your mind? You better. Y equals f of x. I'm sorry, f of x equals x squared. Yeah. F of x equals x squared. We all got a picture of that in our minds. Sorry, guys. Verify that it satisfies the hypothesis of the mean value theorem on the interval from 0 to 2. Is it continuous on 0 to 2?
Yeah.
It's continuous everywhere.
Yeah.
Is it differentiable on the interval from 0 to 2?
No.
Yes, it is. It's differentiable everywhere. Okay. So we verify the hypotheses are met, And then it says, find the solution to this then. Find the C value where this is true. Now, look at the top of page 197 because it shows you the picture, a piece of the graph of y equals x squared that we're looking at from 0 to 2. Notice the black line is the secant. And they've said that the C value where the tangent line is parallel to that is at 1. How did they find that? Well, watch. Let's go ahead and go right here and pretend that the graph is not this one. I'll erase this. We're actually looking at a piece of this graph, as you can see. 2. This over here is 4. Graph that. And they're claiming that at 1, there is a tangent line here that is parallel to that secant. That's what they're claiming. How do we find that? We'll take a look. F prime of C is equal to, what's F of B, where B is 2? What's F of B? 4. What's F of A? 0 over 2 minus 0, which is 2. So we're claiming that F prime of C is equal to 2. We're claiming that there is a C value such that F prime there is 2, because we've simplified this side. Do you understand that so far? Well, what's F prime? If F of X is X squared, then what is F prime of X? 2X. So if I do F prime of X, we're trying to find out the X value where this equals 2, then F prime of X is 2X equals 2, then X is 1. Or in other words, if I go back to C's, C is 1. The derivative of F of X equals X squared when X is C is 2C, and that equals this. We're claiming it equals this, the slope of that secant line, and so C is 1. You want to go through that again?
So you found the slope of the secant line, and then
I found the slope generator and evaluated it at C.
and you C was 2,
And that had to equal the slope of this line,
which was 2.
which was 2.
Okay.
So we found F prime at C. We first found F of X, and I erased all those X's and stuff, and that was very confusing. I understand that. F of X equals X squared. What we do is we find its derivative everywhere. It's slope generator. And evaluate it at C. That's what this is. Okay, so 2C has to equal 2, so C must be 1. That's the value right here. This is C. That's the C value for which the tangent line is parallel to the secant line. Okay? 11.
Thanks.
Be so vocal.
Be so vocal?
Don't
Oh.
stop it. All you guys shut your mouths for a while. That'd be great. All right. Now, I want you to look at the example 2 because this is where it may surprise you a bit. All right. Example 2 says, explain why each of the following functions fails to satisfy the conditions of the mean value theorem on the open or the closed interval from -1 to 1. So we're going to show why these things don't do it, why they don't satisfy the conditions. A part says f of x equals the square root of x squared plus 1. It is just absolute value. You can plug, look at that statement right there. You can plug anything you want in for x. Anything, any positive or negative or irrational or whatever, as long as it's real. You can plug that in because you're going to square it before you square root it. So any value of x will work. And then add 1. That means since the square root of the x squared is x, but you can plug any x in, it's equivalent to absolute x plus 1. It's just an interesting little algebra trick. Y'all see that or not?
Yeah.
What is the conversation, ladies? This can be important here. Listen up. So we have the absolute value of x plus 1, and you see the graph of that at the bottom of example 2. You see it? And we're on the open interval from -1 to 1. The question is it continuous on -1 to 1?
Yes.
Is it differentiable on -1 to 1? No, it fails at 0. And sure enough, there is no tangent line. We already discussed that with the one that was at 0 on the previous page, so that's no news. What was news about it is that the square root of x squared plus 1 is actually absolute x plus 1. Okay. Now look at the b part. It's a piecewise function, and they've got a picture of it for you there too. it says that we're looking at the interval from -1 to 1. Is it continuous on the interval from -1 to 1? That's the first question.
Yeah. No,
Where does it fail?
1.
At 1, which means what?
Not continuous.
It means it's not continuous, yes, but what does that mean about the theorem?
It may
Does
or may
not
not.
apply. Does not apply.
It may or may not.
There may or may not be a C that satisfies this. We discovered in the previous one that there is no C value, where the derivative is equal to the slope. Okay? So we've discovered that it actually fails to have one, but in this one, it actually works out. Now, they don't have a point there for you on that graph. I don't know if I can duplicate this very well, but you're gonna have to use your imagination because it's kind of hard to do this. If I draw this particular graph, I want you to see why this existence theorem, the guarantee doesn't mean that you won't find one if the hypotheses are not met. This thing goes like this. Takes off kind of like that. So on the interval from A to B, we're talking about from 1 to 1 here. -1 to 1. I didn't do that very well. Hang on. So you got to come up like that and then flatten out. Okay. Right here, if I grab that point right there and I connect it to this one over here, this is kind of bad. This has a closed one right here, right? But it's gonna be up here, right there. Yeah, it has a closed one right there. That tangent line right there is equal to 0. If imagine yourself drawing that. Is it equal to 0? Is this one look at the first part of your piecewise function. If we plug -1 into that, do you get 2 for that? This is supposed to be 2.
Yeah.
Yeah, you get 2. And what happens when you plug 1 into the second piece of it?
2.
Yeah, you get 2. Okay, so that means that this is up 2 and this is up 2, so that if we draw this, the slope of that is 0. Wouldn't matter if it was 0 or not, but what I want to know is there any place between -1 and 1 that also has a slope of 0? And the answer is yes, right there. So here a C does exist, where the slope of the tangent line to the curve is equal to the slope of the secant line from A to B.
How would you find that algebraically?
You'd have to take those derivatives and evaluate, well, you'd have to take the derivatives and since you know that this is 0, you'd have to set it equal to 0, which only accounts for the first part, the first piece of it. You set that equal to 0.
The first
I
function
think.
in piecewise.
First function is to 1.
Yeah, because that's one that's less than 1.
Mhm.
And the derivative of that is what?
3x squared.
Plus 3. If you set that equal to 0, because that's what the slope of the secant
Do
line
we
is.
need to bring the +3 for the
No, you don't bring the +3.
Yeah, you're right. You set that equal to 0 because that's the slope of the secant line. You find that x squared is equal to 0, so x is equal to 0. So that's the C value, where
Oh, yeah.
this secant line and this tangent line have the same slope. So we did find a C. Even though that failed to meet the hypotheses, in this case, we did find a C value between A and B, where it was true. So what I'm saying is, you may or may not find one, but you're not guaranteed if the hypotheses are not met. What?
Will there be one where it does not meet the expectations of the hypotheses? And we won't be able to find one algebraically? But there is one there.
Now, this next one, example 3, is really cool because it's interesting because the hypotheses are just barely met, but they are met. Take a look. And I need you guys to get used to this. This is another algebraic thing being introduced that you're going to have to become used to. You all know that x squared plus y squared equals r squared is the equation of a circle,
Yeah.
which is not a function,
Yeah.
right? If I solve this for y, because that's the way we're used to seeing things, I get r squared minus x squared. So y is equal to plus or minus the square root of r squared minus x squared. Except for this is still not a function, it's two functions. It's the top half and the bottom half together as a function. We will always only look at this one. And we won't put a plus sign on it. And r will generally be a number, in this case 1. So in this case right here, we have y equals the square root of 1 squared, which is 1 minus x squared. That's a circle of radius 1, and you need to start recognizing it in this form. Actually, it's a half circle, so that it can be a function. It's the top half of a circle. And you need to start recognizing it in this form where this is the radius squared. And we got y equals, we're looking at just the top half of a circle. So you need to start learning to recognize circles that way. You'll see enough of them that I can hopefully it'll come to you. They've got a picture of it just to the left of example 3. And my question is this function that we're looking at right there, y equals the square root of 1 minus x squared, is it continuous on the interval from -1 to 1? Oh, the closed interval from -1 to 1. It is. Do y'all agree? Is it differentiable on the open interval from -1 to 1?
Yeah.
Okay, is it differentiable on the, just consider this with me for a minute. Is it differentiable on the closed interval from -1 to 1? No, because that 1 and -1 is vertical tangents. But every place else, the tangents have some slope to them, right? So this is what I mean, that the hypotheses are just barely met. But they are met, okay? Which means we're guaranteed. If you connect the circle point from here to here, you get a slope of 0, right? Which means we're guaranteed to have a c value somewhere between -1 and 1, where the tangent line is also 0. It happens to be a 0 because of the symmetry of the circle. But you're guaranteed to find one. The main thing here again was the algebraic expression of a half circle. Get used to it. Okay, here's a physical interpretation. This is kind of interesting too, and I'll give you a better one after we read his. It says if we think of the difference quotient, that is, the change in y over the change in x, as the average change in f over a to b. Are you aware that that's what that is? Let me remind you. The average change over an interval is the slope of the secant line, the average rate of change. Take your first point, your last point, find that slope. That's the average rate of change. Do y'all understand that phrase? Average rate of change. Yes? No. And that f prime of c, meaning the derivative, the slope of the secant line, the slope of the tangent line of c, is instantaneous rate of change. Then the mean value theorem says that the instantaneous change at some interior point must equal the average change over the time interval. That's another way to say it physics-wise. I said that really fast. Let's try it again. The mean value theorem says that the instantaneous change, or velocity if you wish, the instantaneous velocity at some interior point must equal the average velocity over the entire interval. Does that make sense to you?
Yep.
So, if a trucker stops at a way station, and as he's pulling out, they do this, they make a note of the time that he's leaving, and he pulls into the next way station after a certain amount of time, and they clock it, or they write down the time that he pulls in, they can do an average rate of change, right? Because they know the distance between the distance he had to travel between this way station and this one. So they know the total distance. They know the total time as soon as they look that up on the computer. So they can figure out his average rate of change. If that's more than 80 miles an hour, then he was guaranteed to be going more than 80 sometime during that trip. And can be issued a ticket.
I think 70.
Well, you're right. He was speeding.
Those are good.
And you can establish that he was speeding without clocking him with a radar gun.
Kind of sketch.
If you're a trucker and you don't want to get caught, or you're pretty sure that they're looking for you or whatever, then you pull over for half an hour before you pull into that next stop.
Yeah.
Because then your time's, I don't know why you would do that, because you generally, as a trucker, you speed in order to get your load there on time. You risk the ticket. So you don't want to pull over for half an hour because you just lost your,
Risk it for the ticket.
yeah. But if you're sure they're after you, or you're sure that it's some other friendly trucker calls you up on your CD and says, hey, they're watching you. They're looking at times. You want to dodge that ticket and then you deliver your load late, then you pull over for a little while so that the timing on it is, the denominator is longer.
Cool.
Yeah, but you gotta watch yourself. Best thing is make sure that you give yourself a buffer of time before your load needs to be delivered so you don't get penalized there too. Then you gotta decide, are they gonna penalize me when my load is late more than I'm gonna get penalized for the ticket or not? You don't wanna get too many tickets on your record either. They'll yank your license. It's tricky being a trucker.
Yeah.
That was just,
They think that's what I'm gonna use my skills for.
International.
Yeah, there we go.
I'm gonna use
Good
my
skills.
calculus skills.
That's the thing, they'll pull in and the cop will say, you're getting a speeding ticket for this chunk of highway. He says, but I wasn't speeding, you never clocked me, you never saw me. Pulls out his calculus book and says, yeah, but you're not. Yeah.
Well, what the mean value theorem says.
The mean value theorem says you were speeding.
Value.
Mean value theorem is a law.
Okay, here we go, folks. This is where the corollary, you know what the corollaries are to a theorem?
What word?
A corollary?
Corollary.
A corollary is another conclusion that you can make off of the big one. It's a smaller conclusion. And it is the corollaries, not the theorem itself. It's the corollaries that are so important. And you already know the first one. This is actually a definition. It says, let f be continuous. No, let the function be defined on the interval I. That's like from A to B. And let x1 and x2 be any 2 points in the interval. Then, if x1 is to the left of x2, if it's increasing on I, then if x1 is less than x2, then the y value there will be less than the y value of 2. Does that make any sense at all?
No.
All right. The supposition is that the thing is increasing throughout the interval that you're considering. So something like this. That thing's increasing all the time. If I look at it from A to B, then if A is less than B, that's like your x1 and x2. If A is left of B, then f of A has to be lower than f of B if the thing's increasing on the interval. That's what increases means.
Cool.
And you've already been using that. Same with decreases. If x1 is less than x2 or A is less than B, then the y values at x1 has to be bigger than the y value at x2 for all x's if it's decreasing throughout the interval. It's notation.
So this is kind of like, duh.
Yes,
It is, yeah.
it is done.
Okay. I was thinking way over.
It is. Okay, now the corollary that comes in that leads off of that, you've also already dealt with in 4.1. Just review it with me and look at the notation, see if you understand it. That corollary says, let f be continuous on A to B and differentiable on the open interval from A to B. So now, what they're saying is, we've met the hypothesis of the mean value theorem. So let's see if we can figure this out. If the derivative is positive at each point in the open interval, then we can conclude that it's increasing on the closed interval. Does that seem reasonable?
Yep.
If the derivative is negative at every point in the open interval, then f decreases on the closed interval. You've already been using this. This talks about how slopes of the tangent lines, if they're all negative slopes, then the function must be coming down the whole time. We conclude from the calculus that we've got a decreasing function. That first one you said is just a duh. That's actually, and that definition right there is actually a pre-calculus thing. That's why it was a duh to you. And we're taking that idea and applying the mean value theorem to it so that we get the calculus to it, which says if the derivative is always positive in the interval, then it's always increasing. That's our conclusion.
But it's still good right now
Because we've already been doing it, and it's a direct corollary from the mean value theorem. It refers to the hypotheses and everything. It's a direct corollary to that. I can show you why if you want.
Go for it.
I'll do this. I need more.
Why, Axel, why?
So you want to know why this corollary is true?
No.
Yes, please.
I mean, we are not hurt, so it's.
Then I would refer you to 54 on the previous section.
Just believe you.
And if you didn't do that, you may want to take a closer look at it. Because it's all proved right there. And if you want to go through that with me sometime to get your assignment done, or whatever, let me know. If you've already been through it, that's what this corollary is saying. And you proved it already. I can go through it again if you like, although I'd rather not.
We're good.
Look at example 5 then. And look at this function that we're all familiar with again, y equals x squared. It says determine where the graphs rise or fall. It says the A part decreasing on the interval from negative infinity to 0. Because y prime equals 2x is less than 0 on that whole interval. Do you want to take a look at this on the board to discuss it? Do you see what's going on or not?
Oh, I did. Okay. All right.
They're just applying that corollary to a very familiar function. y equals x squared, y prime equals 2x. If we consider the interval from negative infinity to 0, that means any number that I plug in here is going to be negative. That means on this interval, the slope is always negative. That means on this interval, the graph is decreasing. That's all I'm saying. That's all they're saying, and they're applying that corollary to this. Does it make any sense to you or not? Some of you are nodding, some of you are not. Axel, you good on this?
Yeah.
Okay. You sure? You just nod your head. I don't think you were thinking with me when I said it. Can we say it again? Anybody? Okay. All right. B part then says on the open interval, or excuse me, that's open, semi-open. On the interval from 0 to infinity, it must be positive since this same derivative on this interval is plugging in positive numbers all the time. 2 times a positive is positive. So the thing is increasing there. Yes?
Why would it be close interval on 0?
To satisfy, well, because it doesn't matter and it satisfies the theorem.
Okay. So it's like
The closedness of the closed part of the continuousness. You could say the open interval, I wouldn't care. And they don't care on the AP exam, nor do they care on your ISU exam. He is just very, very strictly trying to meet the hypotheses of the theorem in this instance. Okay?
Okay.
All right. Example 6. Determine where the graphs rise or fall. Okay, it says, where is the function f of x equals x cubed minus 4x increasing, and where is it decreasing? You've actually already done several like this in 4.1 because I taught you about sign charts before this section. He doesn't teach you about sign charts till 4.3, but I taught you early. So this should be just like one you did in 4.1. Do you want to do it or not?
Yeah, sure.
Okay, can you read the function to me?
X cubed minus 4x.
X cubed what?
Minus 4x.
Okay, so what's the derivative? What we're trying to do is figure out the intervals for where it is increasing and decreasing. What's the,
2x minus 4.
try again.
3x. Yeah, it's not bad.
3x
3x
squared
minus 4.
minus 4, okay? And then what do we do? What did we do in 4.1 once we got the derivative?
We found critical words.
Critical points by doing what?
Finding where it's 0 and undefined.
And is it ever undefined?
Nope.
This is a quadratic. Okay, so we're gonna look for where it's 0, and that's gonna be x squared equals plus or minus
4/3.
2 over root 3. Well, this is.
X equals.
It's like, hold up.
Yeah, yeah. You're right, 4/3, and then if I square root it, I get plus or minus 2 over root 3. Yeah?
Yeah.
What is this decimal?
Let's see. 1.15.
Okay. Approximately equal to that. Okay? Then what would we do once we found these values where it was 0 and undefined? It's never undefined. What would we do?
Sign chart.
Put it on a sign chart. So we're looking at, so that we get a feel for the size of the number, at negative 1.15 and 1.15. This is actually 2 root 3 over 3 and negative 2 root 3 over 3. Right? You'll notice in the book that he never even square roots the 4. He just puts the square root of 4/3, which is fine too. I really don't like that. I'd really much prefer that you leave it in this form rather than that 4/3. And I really like this form best. Sorry, to be positive. Okay, so what's going on to the left of this in the derivative? Let's try negative 2. It's positive. In between here, try 0. Negative. Over here, it's the same as plugging in a negative one because you're squaring it is positive. So what occurs here?
Max.
A maximum. And what occurs here? A minimum. But what we're really interested in, if you'll remember the discussion what we're having, what we're really interested in is that it is increasing here and decreasing here in this interval and increasing here. That's what we're really interested in from the discussion that we've been having. And look at the graph. This is probably the most important part of this example, is to look at the graph to the left of example 6. The black one is the original function. The red one is the derivative. And notice that where the derivative, the red one, crosses the x-axis is where the black one has a maximum in. Which is exactly what you would expect.
Yeah.
Because this thing right here, this derivative, which is a quadratic, has negative values between here and here. And if the values are negative, then the function itself is decreasing. And where it crosses the x-axis, where it switches from being positive to negative and then from negative to positive. And so if you have a picture of a derivative, just a derivative, like this, like the one we're looking at here. If you have just a picture of the derivative, you can tell, if they tell you this is the derivative, you can tell that right here, that function stops increasing and starts decreasing, because increasing is when the derivative is positive, decreasing is where it is negative. And it stops increasing. I know you're looking at that and go, but it's decreasing all the time. You're not looking at this graph. You're looking at the derivative of a graph. And that if you're thinking about the original graph for which it is increasing here and decreasing here and increasing here because of the positive and negativeness of the derivative. You've got to learn to read a derivative graph that way. That's main thrust of this one, okay?
Slowly.
Okay, I want to jump over to corollary 3. We're skipping corollary 2 because it's, if you think that all this stuff is easy, that was insulting. Okay,
I don't care if you need something if I can do it.
corollary 3. It says functions with the same derivative differ by a constant. This is also duh. Really, truly, when you think about what derivatives are. Here's what it says. Again, notation will get you. It takes a little bit of study to understand and figure out what they're saying. When you do figure it out, you'll go, oh, I knew that. Okay, listen. If the derivative of f and the derivative of g are exactly the same, then there is a constant such that f is equal to g plus c. The original function.
Yeah.
It's just deriving like x squared and x squared.
Right. So it means that if they have exactly the same derivative, then they can only differ by a constant. Do you want me to demonstrate that on the board?
No.
Anybody want to see that?
Okay, so.
But they're making you think backwards now, which is preparation for what's coming, folks. Let me show you about the thinking backwards part. I realize the conclusion is pretty simple. But I want you to think about this right here. Instead of saying, find the derivative if f of x equals g of x plus c, they're not saying find the derivative. They're saying, they're starting you out with the derivative. They're saying if this is true, then this must be.
Is this where we get
And-
into I forgot the C again?
What?
Is this where we get into the I forgot the C again?
Don't forget the C.
Yes, but
Okay.
not quite yet. Not quite yet.
Nah.
What we're saying is,
Yes.
if this, then this must be true. How do you verify it? By deriving this and see if you get this. But they're starting out with the derivative, and they're saying this must be true about the original functions. If this is true about the derivatives, this must be true about the original functions. And you're going, I'm not sure I believe that. Then to verify it, derive this and see. The derivative of f of x is f prime of x. The derivative of g of x is g prime of x. And the derivative of c is 0. So sure enough, the derivative of this is this, which means that if the derivatives are the same, then the original functions can only differ by a constant. Now, is this also true though? If I let k be another constant, is this also true?
Yeah, it is.
Yeah.
Because it's just another constant.
But think about this and the algebra that you've had. If I combine this constant with this one by subtracting k from this one, will I still end up with a constant?
Yeah.
Do we care what it is?
No.
No, because this derivative is 0.
What's the rate?
So that's the reason why they don't offer that, because all the constants have been piled up into that one.
Cool.
Still true. Okay? All right. Let's look at example 7. This is going to be what we call your first initial value problem. And you may want to put a little notation after that So that when it comes to doing an initial value problems in the future, you can refer to this until you've got it down. It's not very hard, but it is a bit new, a bit strange. Has to do with this corollary we just discussed. Here's what it says. Find the function f that passes through 0, 2, and whose derivative is sine x. Now we have to go backwards, folks, because they're going to give you the derivative. Here's the derivative. F prime of x is equal to sine x, and we wish to force it to go through the point 0, 2. By the way, this is like taking a push pin, push pin for a thing, and you've got this function that could be anywhere vertically, because when you add a constant, it moves it up and down. That's all it does, is moves it up and down, right? And so there are millions and millions and millions of functions out there whose derivative is sine x. But there's only one of them that goes through this point. That's a push pin. So whatever function we discover whose derivative is sine x could be anywhere, except for when I take a push pin and stick it right there. This is your initial value. That's what identifies it as a unique function. So if this is the derivative, what is the original? And then what you're asking is, whose derivative do I know of is sine x? Good. Negative cosine x. Right? Plus c. I need to know this c value so that I can put it in the right place. How do I do that? By plugging this in for x and this in for y. That's your initial, that's your push pin. It has to go through that point, which means it has to, at some point on the millions of points that's on there, one of the points has to be 0, 2. And our objective is to solve for c. So once you've discovered this, and don't forget to put your plus c on, because the derivative of this is sine x regardless of what c is, then make your substitutions. 2 equals negative cosine of 0 plus c. Now I have an equation written only in c, and I can solve for that. What's the cosine of 0? 1. So what I now have is 2 equals negative 1 plus c. What's c? 3. So the function whose derivative is this, that must go through this point, is f of x equals negative cosine x plus 3. That function is guaranteed to go through that point, and that function's derivative is this one.
Wow.
The initial value problem. So what you do is, by the way, I'm not supposed to tell you this yet either, but we will because it's easier to refer to it. This process of asking yourself, whose derivative do I know of that is sine? That process of asking that question is called anti-differentiation. Undoing a derivative to the original function. It's an anti-derivative. Find that, don't forget your c, and then use your initial value, this thing right here, this push pin. Plug it in for your y and your x value to find out what c is, and then come back and rewrite it with that c in there. This function goes through this point and has this for a derivative. Do you see it? Okay. That's an extremely important skill. Oh, he does call it an anti-derivative. Sorry. It's right there. Okay? The function capital F. So this is what he wants to say. He's saying, here's a function. Now, pay attention to the notation. Okay? Pay attention to this notation because you're going to need to read it, be able to see it in the book because this is how he refers to it. Instead of calling this f prime, he says it's the derivative of some other function. And he calls it capital F, so it feels like you're going, so that the derivative of capital F is little f. They don't put a derivative on here. They don't put a derivative symbol on it. I know, but you're going to have to get used to reading it.
So much worse.
He's saying, here's a function. Find the function that this is the derivative of that goes through that point. So they're going to offer the derivative as a function itself, not a prime. It's not going to have a prime on it. And they're going to ask you to recover the function that this is the derivative of, and they're going to call it capital F to keep track of which direction you're going. Capital F goes to little f in a derivative, is what we're saying.
Why don't we just put the print?
Because
Things on the other side.
it'll become clear to you again later. I just need you to get used to the notation so that you understand what he's saying here. Okay? So it says right down there in the antiderivative, the function capital F of x is the antiderivative of the function f of x if the derivative of capital F is little f. for all x in the domain. And the process of asking yourself, what function do I know that this is a derivative of, is called anti-differentiation. That's a mouthful. Pressing anti-differentiation. Lots of syllables. Lots and lots of syllables. Okay, one more example. It says we know that if f has one antiderivative, capital F, then it has infinitely many antiderivatives because of the c, each differing from f by a constant. Corollary 3 says these are all of them. That's all there are, just those, which differ by a c. In example 7, we found the particular antiderivative of sine x whose graph passes through 0, 2. It's called an initial value problem. Example 8, now we're going to apply this to a projectile motion problem. Do you remember the relationship between, what's the relationship between position, velocity, and acceleration?
You're right. Each one is the derivative of the other.
Okay, but what do you start? Position. The derivative of position is velocity. The second derivative of position is acceleration, which is the first derivative of velocity. And then there's a jerk, right? But we're not going to talk about that. This isn't going to get jerked around. This one. Here's our scenario. Listen up. Find the velocity and position function of a body falling freely from a height of 0 meters. 0 meters is the top of the cliff, folks. Under each of the following conditions. The acceleration is 9.8, and the body falls from rest. The second situation is the acceleration is 9.8, and the body is propelled downward. So in other words, the first one, the guy's going to hold over the cliff, and he's standing at 0. Wherever the rock is, wherever that height is, that's 0. He's going to drop it, and in the second scenario, he's going to take it and chuck it downward. He's going to give it some velocity as he releases it. Do you understand the difference? Okay. All right, so all we get is acceleration. That's it. What are we supposed to recover? A part, the acceleration. Oh, wait. It says, find each one of the conditions. A part says, we measure the distance. What are we supposed to find? Oh, velocity and position. Oh, so we're given acceleration. We got to go backwards. That's this anti-differentiation thing. So, if acceleration, with respect to time, is 9.8, I'm going to, do you want me to be true to the physics or?
True to physics.
Okay, then it's negative 9.8 meters per second squared. What is the velocity when he drops it?
0.
Well, let's see. Velocity is the antiderivative of acceleration, right? What's the antiderivative of this number? Negative 9.8 t. What?
There is no plus.
Up,
We're anti-deriving.
meters per second.
We're anti-deriving.
Plus C. You forgot the zeros.
Plus c. That's the velocity. And think about that. If you derive this, don't you get this? Okay, now what's the initial condition for velocity in the A part of this problem? Yeah. Time, when time is 0, that's when it's dropped. Initial velocity is 0. So without telling you your push pin point, your initial condition, you have to derive it from there. I mean, you have to get it from there. And so if I let this be 0 and this be 0, what is C? 0. So the velocity in this scenario actually is negative 9.8 t. But we considered the C and discovered it was 0. Do you understand this? Okay. So what is the position function now that we have recovered velocity?
Negative 4.9 t squared. Oh, I see. Okay.
Plus C.
C.
Plus C. Plus C.
Plus C.
Plus
Plus C. Okay. At time equals 0, that's your x value. What was the position?
0.
That's why it was important for him to tell you at the top of the cliff was the 0 point. So the position was 0, at 0. At time 0, position was 0, which means that S of t is what?
At 0.
Negative 4.9 t squared.
Yeah, because C is 0 again. This is a very boring one. Now let's see what happens when we throw the thing down. So now this was the A part. B part, now we have to consider chucking it down. Okay, so I have that the acceleration at the beginning is still negative 9.8 meters per second per second. What is velocity?
T plus C.
Good. And now we have to consider the initial condition. At the time 0, what was the velocity?
1,
No.
0. What did he throw that, guys?
Did he throw it down or up?
Negative one.
Then velocity was negative 1.
Oh,
He threw it down.
said something.
Isn't that what you get from the words that he threw it downward?
Yeah.
Okay.
Yes.
All right. So that means that y is negative 1. This is 0. So c is, so velocity is negative 9.8 t minus 1. That's our velocity function when you huck the thing down.
Uh-oh.
All right? Now, what is position then?
Maybe 4.9 t squared minus x minus t plus c plus
And what was the position in this one when he let it go?
0.
0. At time 0, position was also 0. So if I let this be 0, this y value, and these each be 0, then c is
Minus t from the negative 1 and negative t.
the antiderivative of 1 is negative t. That's why this one works out different.
Why is it 0, 0?
Because at time 0, position was 0. He was chucking it, but at the moment he let it go, his position was 0. And that's when we started the clock.
Okay.
You with me?
Yes.
So if I let this y value be 0, and this be 0, and this be 0, then c is 0. Do you agree? And so this is the position. But it's different from the last one
I agree.
because it was thrust downward at negative 1. And from a position of 0.
Bro.
You with me?
Cool stuff.
So this one turned out slightly different than that one. What?
Do you antiderive it even more? Like, is there like a third antiderivative? Like,
No, I do not know what the antiderivative of position is in a physical sense. I don't know what that is. If someone has interpreted that, I don't know what it is. I haven't heard it in a physics class. Okay. And there you go. You guys, the math on this will be very easy. Concepts are very important.
Don't forget the c.
Happily, they're not so hard. So whoever's watching, hope you have fun with it. Bye.
Thank you.